Gas laws. Dalton's law of partial pressures. Of all the gas law formulas that you will learn about in saturation diving, possibly the most important of all is Dalton's law of partial pressures.
Okay, today we're going to talk about oxygen. We're going to talk about Dalton's law. Okay, but before we get into Dalton's law, we need to have a general understanding about oxygen. Now, oxygen supports life. It's crucial to life. We all need oxygen. And generally speaking, more oxygen can be better than not enough. But what you do need to realize when it comes to saturation diving, there is 4 ways that oxygen can actually kill you, or it can severely harm your health. I'm going to list them now. So you can have chronic, you can have acute, you can have hypoxia, and you can have anoxia. So let's start with chronic oxygen toxicity. Now, I've had chronic oxygen toxicity, and I'm going to give you a quick story. Okay, 30, 40 years ago, we did a lot of bell bounce diving. I was doing a 450 foot on a Yankee 500 table. When we did the dive, it's meant to be a 13-hour dive, half an hour on the bottom, and then 13 hours decompression. But when we got to about 100 feet, my bell partner and I started to suffer decompression illness symptoms in our arms. And then by the time we got to 60 feet, we had to extend it by 6 hours, 5 or 6 hours to do a treatment table. So we had a lot of extra oxygen. Now that oxygen gave me burning of my lungs. And by the time we finished 17 hours, we had burning in our lungs, damaged lungs, painful to breathe. It took a few days to recover, but that's what chronic oxygen toxicity feels like. I've actually had that. Now, there's another type called acute oxygen toxicity. Now, in the hyperbaric industry, for example, we treat patients on 100% oxygen. It could be divers, it could be people with non-healing wounds. When they're breathing pure oxygen at 2 and 3 atmospheres absolute, they can have a fit. They pass out and have a fit. Navy divers that breathe oxygen sets can happen to them in the water, can have an oxygen fit. We had a lot of oxygen fits in surface mixed gas diving, and that's when it's acute, it's because it's very quick. Acute means quick, chronic means slow. So acute oxygen toxicity, you will pass out. Okay, so if you get too much oxygen, it can make you pass out. Pure oxygen will do that to you. Hypoxia is not enough oxygen. Anoxia is no oxygen. So there's 4 cases of oxygen there which can be life-threatening. Now, it's essential that we have a quick and reliable way to measure oxygen at all depths, and that's where Dalton's law of partial pressure comes in. We're going to get right into this. It's the most important thing you're going to learn in saturation diving.
Okay, the definition of Dalton's law of partial pressures. Partial pressure is the pressure that a single gas in a mixture would exert if it alone occupied the entire volume. This may be a difficult concept for you to grasp. So the main thing to understand is that we must use partial pressures in order to make it easier for you to measure, to monitor, and to quantify each individual gas. Dalton's law deals with inert gas, that's nitrogen and helium uptake, oxygen toxicity, nitrogen narcosis, carbon monoxide poisoning, carbon dioxide poisoning. But in this presentation, we're primarily concerned with the partial pressure of oxygen. In saturation diving, control of oxygen, or O2, is crucial. We're focusing on oxygen because oxygen, if not well managed, can hurt us, divers, in many different ways, particularly sat diving. Here are some of the ways. Chronic oxygen toxicity, or pulmonary oxygen toxicity, because it affects the lungs. Acute oxygen toxicity, which is central nervous system toxicity, which is often brought about by very high levels of oxygen or pure oxygen. hypoxia, which is lack of oxygen, not enough to support life, and anoxia, which is no oxygen whatsoever. Also, O2 flammability in the atmosphere is a potential fire and explosion, which often happens in the shallow range of the saturation dive when you're decompressing. Okay, so the only way to measure and control oxygen content and hazards is by having a strong understanding of partial pressure of oxygen formulas. So to start with, let's first understand partial pressure in air diving.
Air is mainly made up from two gases, oxygen and nitrogen. 21% of air is oxygen, and 79% of air is nitrogen. The atmospheric pressure at sea level is 1 bar. So, 21% of it comes from oxygen, and 79% of it comes from nitrogen. We call the pressure exerted by each gas the partial pressure, because it is part of the total pressure. In air with 1 bar of pressure, the partial pressure of oxygen is 0.21 bar, and the partial pressure of nitrogen is 0.79 bar. And together they add up to 1 bar. When you go down underwater, the total pressure gets higher. This means the partial pressure of each gas also gets higher. For example, if you go down to 10 meters of seawater, the total pressure of air you are breathing goes up to 2 bar, double of what it was at the surface. This means the partial pressure of oxygen and nitrogen will also be double of what it was at the surface. To find out what the new partial pressure of each gas will be, multiply the decimal percentage of the gas by the total or absolute pressure at depth. So, at 10 meters depth where absolute pressure is 2 bar, the partial pressure of oxygen is 0.21 multiplied by 2, which is equals to 0.42 bar. And the partial pressure of nitrogen is 0.79 multiplied by 2, which is equals to 1.58 bar of pressure. If you add them together, 0.42 and 1.58, you should get back 2 bars, which is the total pressure. Note that the percentage of the gases does not change. Oxygen is still 21%, and nitrogen is still 79%. But the pressure that each gas exerts goes up, because the total pressure goes up. This is important because some gases become very dangerous when they reach a certain partial pressure, which becomes toxic when breathed, resulting in adverse physiological effects. This includes oxygen.
Measurement and control of partial pressures may be more easily understood if you use the T formula method. The T formula is illustrated here as PPO2 over absolute pressure on the left and decimal percentage on the right. You can see there's a T there, so we're dividing or we're multiplying. That's what makes this method easy to understand. Okay, the simple method to solve partial pressure problems is to arrange the variables in a T formula. To use the T formula, there can only be one unknown value. Multiply the known values if the unknown value is partial pressure, or divide if the unknown is absolute pressure or gas percentage. Using the T formula method, either first multiply then divide by 100, or first divide then multiply by 100. That's easy to remember, isn't it? Here's an example using air at 10 meters or 33 feet of seawater. What is the PPO2? Okay, on the bottom left there, we've got 2 atmospheres absolute multiplied by 21%. So 2 times 21 is 42. Divide that by 100. That gives us 0.42 PPO2. That was fairly easy, wasn't it? We can go back the other way. So given the PPO2 at the top at 10 meters of salt water, what's the percentage? 0.42 divided by 2 times 100 gives us 21%. It's pretty simple, isn't it? Let's try some more examples so you can become familiar with PPO2 formula. The partial pressure formula is partial pressure equals absolute pressure times decimal percentage. The decimal percentage is the percentage divided by 100, or move the decimal point back 2 spaces. For example, decimal percentage of 15% equals 15 divided by 100 equals 0.15. Or move the decimal point back 2 spaces, i.e. 15 equals 0.15. Okay, here's the example number 1. A diver at 40 meters is breathing 2080 nitrox mix. What is the PPO2 in his mix? Step 1, find the absolute pressure. There we go, depth in meters divided by 10 plus 1. That's 40 divided by 10 plus 1 equals 5 bar absolute. Step 2, find the decimal percentage. Oxygen percentage is 20%. Decimal percentage equals 20 divided by 100 equals 0.2. Step 3, substitute the known values into a formula. That's partial pressure equals absolute pressure times decimal percentage. Simple as 5 times 0.2 or 1.0 bar absolute. There's the answer. Partial pressure in his mix is 1.0 bar absolute. Another example. A diver at 250 feet of salt water is breathing 15% in his mix. What is the PPO2? Step 1, find the absolute pressure. Depth in feet of seawater divided by 33 plus 1 atmosphere. So there we go, 250 divided by 33 plus 1 equals 8.5 atmospheres absolute. Step 2, find the decimal percentage. 02%, 15%, divided by 100, 15 divided by 100 gives us 0.15. That's the decimal percentage. Step 3, substitute the known values into a formula. Okay, partial pressure is 8.58 times 0.15 equals 1.287 atmospheres absolute. So the PPO2 in his mix is 1.287 atmospheres absolute. Another example. If the PPO2 must lie between 1.2 and 1.4 bar, what is the greatest depth at which a 15% mix could be used? Step 1, find the decimal percentage. So the O2 is 15%. Decimal percent is 15 divided by 100 gives you 0.15. Substitute the known values into a T formula. So we've got 1.4 is the PPO2, the highest end, and we divide it by 0.15, which we know is the decimal percentage. 1.4 divided by 0.15 equals 9.33 bar. There we go. So step 3, convert the absolute pressure to depth. 9.33 bar minus 1 times 10 gives us 83.3 meters of seawater. We've got an answer. Maximum depth at which a 15% mix can be used is 83.3 meters of salt water. Another example. During a bounce dive to 80 meters of salt water, the divers require a PPO2 between 1.2 and 1.4 bar. What is the suitable mix? Step 1, find absolute pressure. And we can see how it's done right there. 9 bar absolute. Substitute known values into a formula. PPO2 of 1.4 divided by 9. Decimal percentage 0.1556. Convert to decimal percentage gives us 15.56%. So the maximum oxygen percentage allowed is 15%. Now just note, when rounding up or down decimals, one should always do so to the factor of safety. For example, in this case, rounding 15.56% to 16% would result in a higher PPO2 of 1.44 bar, exceeding the allowable PPO2 limit of 1.4 bar. So the correct answer for the mix, therefore, is 15%, as it would not exceed the 1.4 bar PPO2 limit at the maximum depth of 80 meters. Okay, carbon dioxide. Calculations of partial pressure of carbon dioxide, or ppCO2, are often carried out using parts per million. Here's an example. Chamber is at 80 meters of salt water. The carbon dioxide reading, as read at the control room analyzer, is 400 parts per million. What is the partial pressure of CO2 in the chamber? An alternate way to calculate it is as follows. Partial pressure of CO2 expressed as a percentage. Here we go. 400 parts per million divided by 10,000 gives us 0.04% CO2. The absolute pressure, that's the depth plus 10 meters of salt water, is 90 meters of salt water. So partial pressure is 90 times 0.04, which gives us an answer of the ppCO2 is 3.6 millibars. We're going to get into this later in the course, but that gives you a basic understanding of it. Try and remember this and keep it with you so when you get to the saturation diving phase, you can better understand it. Oxygen partial pressure limits. It was suggested in the past that divers underwater can breathe gas containing a partial pressure of up to 1.6 bar with minimal risk of toxicity. A number of regulations, international guidance documents, IMCA, OGP, have reduced this figure to give extra safety factor. IMCA now recommends 1.4 bar is used as the upper limit for partial pressure of oxygen in a nitrox mix breathed by a diver when at a depth if using surface applied techniques. That's surface applied. Now the bottom point here, the Diver Medical Advisory Committee, DMAC, recommends that the maximum PO2 supplied to the diver from the bailout should be 1.4 bar, and that's in DMAC 04. Oxygen partial pressure limits. In the supervisor's manual, D022, recommended oxygen partial pressure limits are therapeutic treatment 1.6 to 2.8. That's if you are treated in saturation and you need to do higher level of oxygen whilst you are being treated in the chamber, in a similar way that you would do a table 6 for an air diver on pure oxygen. In the sat chamber, you would use a mix of 1.6 to 2.8 bar, and you'd have cycles of 20 and 5. Different companies have different schedules. Bounce dive, the partial pressure limit would be 1.4 bar. Saturation in the water, 0.5 to 0.8 in the bell and in the water. Saturation in the chamber, 0.35 to 0.5 bar in the chamber. CDA uses 0.5. Bailout cylinders 1.4, and maximum for surface supply diving is 1.4 bar. So in summary, the partial pressure is the pressure that a single gas in a mixture would exert if it alone occupied the entire volume. The sum of the parts equals the whole. Lastly, in a gas mixture, the portion of the total pressure contributed by a single gas is called the partial pressure of that gas. Try and remember the T formula. I find that's the easiest way to do this and the easy way to remember it. There it is right there in front of you.